Hello friends, today we will learn about Gauss-Legendre quadrature, a better way for numerical integration. So this quadrature method is better to what? Compared to what methods these are better I am saying. So in general we do our numerical integrations with trapezoidal rule, Simpson 1/3 rule, Simpson 3/8 rule, and so on. So these all are a general thing. So this is called Newton-Cotes formula, and this Gauss-Legendre quadrature method is better than Newton-Cotes. So I am Shubhadeep from IIT Kanpur. Let me start. So first we should know about the degree of precision. If the integration rule can give you the exact result for any polynomial of degree r, but it produces some non-zero error for some polynomial of degree r plus 1, then r is the degree of precision for the integration rule. So what we in general use, that is the trapezoidal rule or Simpson 1/3 rule. So for trapezoidal rule the degree of precision is 1. So that means what? That means you can integrate a linear function exactly with trapezoidal rule, but whenever you will use some quadratic polynomial, then the trapezoidal rule cannot give you the exact result. So for that you have to go for Simpson 1/3 rule. So because Simpson 1/3 rule have the degree of precision is 2, and you can integrate up to the quadratic functions with Simpson 1/3 rule. So in general the form of this approximation is integration over a to b function fx dx is equals to some weight function. These are called weight factors. So these wi's are the weight factors, and these functions value at some sample points, those are xi's. So xi's are called sample points and wi's are called the weight factors. So in general this is for the endpoint formula. So for trapezoidal rule, so this basically n is equals to 2 here. So we can just revisit our Newton-Cotes method. So we choose n equispaced sample points in the interval of a and b, where my sample points xi's are a plus ih, where h is the segment length. So b minus a is the total length, the total integral interval, length of the integral interval, and n minus 1 is the number of segments. If I have n points, then n minus 1 is the number of segments. So now you can calculate the sample points. Now you can form this n equations such that the rule gives you the exact result for the polynomial functions fx is equals to x to the power k, because you have n unknowns, because you know all the sample points xi's, but you don't know about the weight function. So how many weight factors are there? N. So n weight factors are unknown. Now n weight factors are unknown, so you can calculate them, you can determine them from this n equation, such that you can have these functions like x to the power k, where k is 0 to n minus 1. So k is 0 to n minus 1 means k can be, basically this function can be can have n number of functions you can form. So with this you can just form, with the linear superposition of these functions, you can form any kind of polynomial of degree n minus 1. So you can, if the rule gives you the exact result for this polynomials like fx is equals to x to the power k, then it will give the exact result for the polynomial of degree n minus 1. Okay, so one can solve this n weights from these n equations, and then you are done, because you know the xi points, you know the wi is the weight factors, then you can just calculate up to n minus 1 degree. You can integrate with your rule. So that is why when you have this for trapezoidal rule, you can just put capital N is equals to 2, then you can just integrate up to n minus 1, that means the power 1, so that means linear function. And for Simpson 1/3 rule, your n is 3, so that means with Simpson's 1/3 rule you can just go up to the quadratic function. Okay, so just for example, I am showing the trapezoidal rule. The sample points are x1 is equals to a, x2 is equals to b. So for that you can just have k can be 0 and 1. So x to the power 0 means 1, x to the power 1 means x. So now your exact calculation of these integrations will give you that for the 1, if the fx is 1, then integration of fx dx from a to b is equals to b minus a, and similarly this is half b square minus a square. And if you write this formula with these weight factors, so in this case it will be for the case of function fx is equals to 1, it will be w1 plus w2, because f at a is equals to 1, f at b is equals to 1. And similarly for the case of fx is equals to x, then the w1 multiplied by f a, that means a, and plus w2 multiplied by f b, that means b. So this is w1 a plus w2 b. One can solve this weight for with this equation, but by equating this, so w1 plus w2 is equals to b minus a, and w1a plus w2b is equals to half b square minus a square. So you can solve them because two equations are there and two linear equations, and you can easily solve them, and you can get w1 is equals to w2 is equals to b minus a by 2. And with this, your formula is the integration over a to b fx dx is equals to the weight factor. Since both of them are equal, so I have just take it common, and so b minus a by 2 multiplied by fa plus fb. So this is exactly the trapezoidal rule, you can see. So similarly, if you can do it as a homework, so you can do the same procedure to calculate the weights for 3-point rule, and you will get, so for 3-point rule the equispaced points will be like x1 is equals to a, x2 is equals to a plus b by 2, x3 is equals to b, and just write the formula for the integration. Your answer will be like w1 is equals to b minus a by 6, w2 is equals to 2b minus a by 3, w3 is equals to b minus a by 6. You can just check it out in your home, and you can check the integration formula will be like this. So you can see this is exactly the Simpson 1/3 rule. So whatever you have done in your Newton course exercise, so this is the thing. So you can just put n equals to 3, and you can get the Simpson 1/3 rule. If you put n is equals to 4, then you can get Simpson 3/8 rule. Now, any better option? So we have constrained ourselves to the case where sample points are known and equispaced. So whatever we have done now, so these xi's were known in the interval of integration. Now what if they are unknowns? Then you have total 2n number of unknowns, because now n number of xi's are unknown, n number of weights are unknown, that is wi's. So now for 2n unknowns, to determine this 2n number of unknowns, we need 2n number of equations. So we can form 2n number of equation and solve for 2n unknowns such that my any polynomial like x to the power k, where k can be 0 to 2n minus 1. So we can integrate exactly up to the polynomial of degree in 2n minus 1. So this is 2n minus 1. So this is obviously a better option, because with n points you can go up to n minus 1 of the n minus 1 degree polynomial. Now with n points, the same n points, you can go up to 2n minus 1 degree of polynomial. So your polynomials degrees are increasing with the same number of points, so that is a very good advantage. So now you can go up to third degree polynomial exactly with 2-point rule, where you can do only the linear functions before with Newton course. So for 2-point rule, let me just show you that I have just put a is equals to minus 1 and b is equals to 1, which makes our life simpler. And for this we have just make the table in the similar way. So the functions are as now I am using 2-point rule, so capital N is equals to 2, so therefore we can my k can be go from 0 to 2n minus 1, so 2n minus 1 is 3, so here because n is equals to 2, so 3. So we have gone through these polynomials and our exact results are here. You can just check it out with the analytical result, these are same. So now I can write with this formula that w1 and w2, x1 and x2. So here 4 number of unknowns are there. So w1 plus w2 is in the first case. In the second case, w1 x1 plus w2 x2. Here I don't know about x1 and x2, so I have to write them. And you can just form 4 equations now. See that w1 plus w2 is equals to 2, w1x plus w2 x2 is equals to 0, w1 x square plus w2 x2 square, sorry, w1 x1 square plus w2 x2 square is equals to 2 by 3, w1 x1 cube plus w2 x2 cube is equals to 0. So you can form 4 equations, and now with these 4 equations you can solve x1, x2, w1, w2. So these 4 unknowns you can solve, and from here you can easily solve them, that w1 is equals to w2 is equals to 1, and x1 is equals to minus 1 by root 3, and x2 is equals to 1 by root 3. But you can see that here x1 and x2 are non-linear. So if you use more than 2 points, so if you use 3-point rule, you can use 4-point rule, so then it will be difficult to solve them. And it's really difficult. Okay, so what we can do, we will see, but before I go to the general case, just do an example. So let me just do the integration I is equals to minus 1 to 1, integration over minus 1 to 1, and the polynomial is 3x cube plus 2x square plus 4x plus 5 and dx. So this is a general third degree polynomial. So as I am using 2-point rule, so I can go up to third degree polynomial. Okay, so now I can write this weights are 1, so this is 1 multiplied by the function at a, and plus w2 means 1 multiplied by function at b. So this is the function at a plus this is the function at b. No, sorry, not a and b. Obviously it is at x1 and this is at x2. So x1 is equals to minus 1 by root 3 and x2 is equals to 1 by root 3. So we have just compute it, and from here you can see some of them will be cancelled out, like this cubic terms and the linear terms will be cancelled out, and you can just end up with this result. So this is 4 by 3 from this squared term, and this 5 plus 5 is 10, so you can ultimately get 34 by 3. So this is the result of your integration, and you can just check it with the analytical solution also. So now you can see that you can go up to third order polynomial, and this is you can do this will give you the exact result. Okay, now I go to Gauss-Quadrature theorem. So if we, as I am talking about, that if you increase n, then these equations will be highly nonlinear, and it will be difficult to solve. So now I'm just stating this theorem that let qx is a non-trivial polynomial of degree capital N, such that the integration over a to b x k qx x to the power k qx dx is equals to 0, where k can be from 0 to n minus 1. So this x to the power k should be some can be the polynomial of order n minus 1 up to n minus 1, and qx is equals is some n degree polynomial. So if they are 0 and this x1 x2 to xn be the zeros of qx, so that means as qx is a polynomial of degree n, so it have n number of solutions, n zeros. So at n values of x, this qx will be 0. So these x1 x2 xn's are the zeros for zeros of qx. Then this integration formula, that a to b fx dx, is this is approximated obviously, but this will be exact for any polynomial up to degree 2n minus 1. So we have to prove that, and where this wi is equals to, this weight factor is equals to integration over a to b, and this curly li is the Lagrange interpolating basis. So this li is the so this is the n minus 1 order polynomial. Okay, so you can see that if this is a successive multiplication, and as I not equals to 0, so it goes up to 1 to n, but j not equal to I, so that means it will be multiplication of this kind of term n minus 1 times, so it will be a n minus 1 order polynomial. Okay, so this is the Lagrange interpolating basis. So now let me prove this. So let fx is equals to px qx plus rx. So where rx and px are the n minus 1 order polynomial, and this qx is n order polynomial. So then just tell me this what is the degree of this fx polynomial. So fx polynomial will be must be 2n minus 1, because this is n minus 1, this is n, so this is 2n minus 1 because here multiplied, and rx is basically n minus 1. So overall this polynomial is 2n minus 1. Now if we integrate from a to b, so this part will become 0, because by the choice of qx, because I choose such qx such that this px qx integration over a to b is 0. Now so this fx integration over a to b is equals to rx integration over a to b. Now I am just approximating, actually I am not approximating, it will be true for any polynomial of r minus 1, because this is a n-point rule, n-point Lagrange interpolating rule. So I can just approximate this rx with any rx function with this rxi point and this lix. So these are the Lagrange interpolating basis polynomial. So this is n minus 1 order polynomial, and you can see this is a constant. So you can, in this way you can just, from this Lagrange interpolating basis, you can construct this rx function, and for if rx is the polynomial of degree n minus 1, this n-point Lagrange interpolation is exact. So I can just exactly write in terms of this interpolating basis, and instead of rx I can write this sum, and you can see that this you can write this a to b lix dx is equals to wi. So that is the weight. So you can just write like this, wi's are a to b lix dx, and you can see if you choose this sample points to be n roots of qx, so qxi equals to 0, then then fxi is equals to rxi. Okay, so because this pxi and qxi is 0, because xi's are roots of qx, so that was stated in the theorem too. So now we can just write fxi instead of rxi, and your lx dx integration over a to b is w, the weight factor. So now you can write this integration over fx dx is exactly same as the wi fxi. So if you can choose such qx, that is the nth order polynomial, you can choose in such a way that this integration becomes 0, and you can choose the sample points xi as the roots of this polynomial, of the polynomial qx, then it will be exact. So this is proved. Now all we need to find is the polynomial qx. Okay, so then we can proceed for its roots, and hence I can just compute the wi weights. Now, so just look about some orthogonal polynomial concept. So orthogonality of the two functions on the interval a to b is given by this. So a to b integration over gx hx dx is equals to 0. Then it calls the gx and hx are orthogonal on the interval a to b. So we can use the roots of orthogonal polynomials. Okay, so for example, I am just talking about Legendre polynomials. These are, and the interval is -1 to 1. In this case, these polynomials are defined as p0 is equals to 1, p1x is equals to x, p2x is equals to half 3x square minus 1, and so on. So they can be generated from the recurrence relation also. So if I give this p0 and p1, you can generate any order polynomial. Okay, so and you can see that previous sample point solution were the roots of p2, because we have used the 2-point rule. Okay, so for 2-point rule it was you can see that this is the solution, so plus minus 1 by root 3. So you can see is there any connection between them or not. So obviously, definitely we have. So orthogonality of Legendre functions on the interval -1 to 1 is given by this plx pmx integration over -1 to +1 is 2 delta lm divided by 12 plus 1, where this delta lm is called Kronecker delta. It will be 1 if L is equals to m, and if L not equals to L, then it is 0. So for if I use any polynomial of degree n-1, okay, any polynomial of degree n-1 can be represented on this interval as the px is equals to ci multiplied by this Legendre polynomial. So we can expand any function, any polynomial function, in terms of the superposition of Legendre polynomials. So now if px is sorry, this small n should be the capital N. Okay, so this px is capital n-1 degree polynomial. So from the orthogonality property we can say this, because this in this expansion the Legendre polynomial can be of the order of at max n-1. So with this p capital N, it will be 0. So there will be no pn. Okay, so that is why this integration will be 0. So for using this n points formula, we can use the Legendre polynomial, this qx is equals to pnx, p capital Nx, and we can use the n roots of this p capital Nx as the sample points, and we can compute the weights accordingly. So with this we can integrate any polynomial of degree 2n-1 exactly. So what can be done for general integration limits a and b, because whatever we have done now up to now, so we have done only with this -1 to +1, because we have not we put a is equals to -1, b is equals to 1, so we have not shown this in general case, but what if because in our real life the integration cannot be like only -1 to +1, it can be +3 to +5 or something like that. So for that we can just change our we can just transform our coordinate and we can do the thing. So what is the procedure? Let me show. So for a general limit of integration, we need to calculate a to b fy dy. Okay, and give a linear transformation such that the limits become -1 to +1, so that we can just use the Gauss-Legendre Gauss-Legendre integration quadrature. So now let us write yx is equals to mx plus c, where y minus 1 is equals to a, y1 is equals to b. Then we get this y is equals to b minus a by 2 x plus b plus a by 2. Then integrate using the old formula with limits -1 to +1, because I can just write this integration with this transformation. Instead of y I can just write it, and instead of dy I can just write b minus a divided by 2 dx, and my limits will be changed to -1 to +1. Then I can just easily use this formula, use the integration. Then we can just write xi's instead of x here, and our integration will be done. It is very easy. So for example, let us calculate this I is equals to 0 to 1, so this is not -1 to 1, this is 0 to 1. So y square by dy, y square dy, so its answer is 1 by 3. It's very easy. But let us check with this transformation. So for this case, b minus a by 2 is half, b plus a by 2 is half. So we put this transformation, y is equals to half x plus half. Therefore this 0 to 1 fy dy is equals to half, because b minus a by 2, this should be here, and then instead of y I can write just half x plus half dx. Then I just put the 2-point formula. So this is 2-point formula, so I can just write half multiplied by f of this -1 by 2 root 3 plus half of half into f of 1 by 2 root 3 plus half. So as the function is y square, so I have to just square it, and then my result is 1 by 3. You can just check it out with your pen and paper, and you can see this will give you the exact result. So this is a very powerful technique, that if you use Gauss-Legendre quadrature formula, then you can just go up to 2n minus 1 degree polynomial with just only n points. Okay, so this is exact result. So in conclusion, we have revisited the integration schemes like trapezoidal and Simpson 1/3 rule, used the equispaced sample points but undetermined weights, and shown that trapezoidal and Simpson 1/3 rule as special case with the number of points 2 and 3 respectively, because they are basically Newton codes. And then we generalized and extended the idea by making the sample points undetermined along with the weights. Then we proved the Gauss quadrature theorem and shown the connection with Legendre polynomials and numerical examples and solution for the general integration limits, that we can integrate not only for -1 to +1, we can go for a to b in general. So that's what the Gauss-Legendre quadrature, and thank you.